Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, you will learn the covariance of two random variables. So previously, you have learned how to join the two random variables, or we call it bivariate random variables. Okay, you find the joint distribution function, you find the marginal and conditional density function, and then you look either this joint distribution function independent random variables or not. Okay, and then there are expected value and variance of the bivariate random variables. So in this video, you will learn the covariance of two random variables. So if you look definition 5.10, if y1 and y2 are random variables with means mu1 and mu2 respectively, the covariance of y1 and y2 will be this equation. Okay, so if you look this equation, we denote by COV, which is covariance of y1, y2 given expected, y1 minus mu1, y2 minus mu2. So if you remember, last semester you have learned correlation, isn't it? So you can see that you have y1 is your x1, for example, and then you have y2, the second variable, okay, the second random variable. So you can see you have this covariance. Okay, you can see the mu is in the middle for mu1 between, and then mu2 for this one. Okay, so this is the data. Okay, so in this case we have positive correlation. Okay, you can see the data is moving towards to the right. Okay, but if you look at picture B, this one is independent random variables. That means the between y1 and y2 there is no correlation, so there's no covariance. Okay, so it is difficult to employ the covariance as an absolute measure of dependence, okay, because its value depends upon the scale of measurement. So as a result, it is difficult to determine at first glance whether a particular covariance is large or small. So basically, if you look this figure, you can see there is a correlation, there is a covariance, but we cannot see how much is the difference, okay, because it's difficult to measure, okay. Therefore, we can standardize this by using correlation coefficient, which is rho, okay, a quantity related to the covariance and defined as this equation. So if you remember before this in applied statistics, you learn how to find R, isn't it? So this R is for sample, but this one is for population. Okay, so where here if you look, sigma 1 and sigma 2 are standard deviation of y1 and y2 respectively. Alright, theorem 5.10. If y1 and y2 are random variable, which means mu1 and mu2 respectively, then the covariance for y1, y2, okay, you have this from previous theory, but this one you will get this expectation, okay, expectation of y1 y2 minus expectation y1 times expectation y2. So this one can be proved. So if you look here, you have covariance y1 y2 and then you have this one. So this one you multiply, okay, multiply as usual, so you will get this equation, okay, and then base theorem 5.8, this one you can split it up, isn't it? So once you split it up, you will get here, this is expected y1 y2 minus mu1. Okay, this one expected mu1, but this is a constant, then you get the mu1 as well, and then you have expected y2 minus mu2 expected y1 plus mu1 mu2. Okay, and then you remember, if we have expected y1, this is actually mu1. If you have expected y2, this is actually mu2. So based on that, you substitute the value. So here mu1 mu2, here mu2 mu1. So you can see this one you can cancel it out. So finally you will have expected y1 y2 minus mu1 mu2. Okay, so this one something wrong somewhere here, the notation. Okay, but you can this one the other way, similar. This one you cancel out, then you get this one. Okay, so it doesn't matter mu1 mu2 or mu2 mu1, you will get the same answer. Okay, but then when you cancel this one, you get this one. So it's proof. Okay, it's proof. Then example 5.22, refer to example 5.4, find the covariance between the amount in stock Y1 and amount of sales Y2. Okay, if you remember, this one we have gasoline. Okay, so recall that Y1 and Y2 have joint density function given like that one. Okay, 3Y1, and then Y2 is less than Y1 because Y1 is a supply. Y1 is Y2 sales. Okay, the sales should be smaller than the stock. Okay, and then Y1 is between 0 and 1. So if you look here, in order to find the covariance for Y1 and Y2, you will have this one. And then again, here is the formula. Okay, you have Y1, Y2, which is come from here. And then this is your FY1, Y2, the joint density function. Right? And then you integrate as usual. Okay, in this case, we integrate with respect to Y2 first, then Y1. And then you substitute the value. Then you get 3 over 10. So if you look here, this one from previous, you get 3 over 10 here. Okay, and then minus 3 over 4 times 3 over 8. Then finally you get 0.02. Okay, because the question asks you to find the covariance. So the covariance is this one lah, covariance Y1, Y2. And then based on this covariance Y1, Y2, you have this formula, isn't it? So that's why you need to find this one first. And then this one based on previous example, you just have to take the value. So in this example, large value of Y2 can occur only with large value of Y1. Okay, because there is a relationship behind it lah, among Y1 and Y2. And the density, okay, the joint density is larger for larger value of Y1. Okay, you can see this one from figure 5.4. And then it is intuitively that the covariance between Y1 and Y2 should be positive. Okay, so that example, 5.22. Okay, so if you look, the answer is 0.02 lah. Okay, and then if you look example 5.23, okay, page 267, let Y1 and Y2 have joint density given by this one. So you have this joint density function. Find the covariance of Y1 and Y2. So again, you will have this formula. Okay, and then you look, based on example 5.15, you have this value. And then example 5.16 and example 5.17, you get the value. So you just substitute the value and then you get 0. So if you get 0, what does it mean? Okay, based on our previous dimension, if covariance equal to 0, that means it's an independent random variables. All right, but there is a theorem 5.11. Okay, if Y1 and Y2 are independent random variables, that means covariance Y1 and Y2 will be equal with 0. Okay, thus independent random variable must be uncorrelated. Okay, because it's independent random variable, isn't it? There's no correlation between these two variables. So the covariance should be equal with 0. So the proving, you have theorem 5.10. Okay, establish that we have this one. Okay, then because Y1 and Y2 are independent, okay, so this one just you get like this lah. Okay, because theorem 5.9 is implies. Okay, if you look theorem 5.9, okay, this one, this is from previous. Okay, this one, this is called independent when you have like this. Okay, if independent you have like this, then that's why based on that theorem you can have this one. Okay, now we look at example 5.24, page 267. So let Y1 and Y2 be a discrete random variable with joint probability distribution as shown in table 5.3. So this one, show that Y1, Y2 are dependent but have 0 covariance. That means Y1 and Y2 there is a correlation. Okay, they are correlated, but the covariance of these two random variables is equal with 0. So if you look the table here, we can calculate the marginal distribution probabilities for the Y1 and Y2. So if you look here, if we have P1 negative 1, this one, and then P1 1 here, so here you will get 5 over 15, 5 over 16, okay, here. 3, 1, 4, 3, 4, 5. So 5 over 16. This one also you get 5 over 16. And then that one also for P2 negative 1, P2 1, you also get 5 over 16. Here also 5 over 16. And then if you look P10 here, you get 6 over 16. And then here you also get 6 over 16. Okay, but the value for P00 you get 0. Okay, obviously at P00 it doesn't mean P10 times P10. Okay, because this is show that it's dependent. Okay, because you can see that this one you get 0, isn't it? However, P10 is equal with what? P10 equal with P10 equal with 616. Okay, that's mean if you look here, you get 6 over 16 times 6 over 16. So this one not equal with 0. So it's obviously seen that this is not independent. Okay, it's a dependent. Okay, so again, looking at the marginal probabilities, you can see that expected y1 equal with expected y2, which is equal with 0. Okay, this one, if you want to find using the covariance formula, this one, you can calculate this one. Okay, so if you calculate this one by using this formula, you will get 0. Okay, and then minus expected y1 you get 0, expected y2 you get 0, and covariance is equal with 0. So the covariance is equal with 0, but based on this one, these two random variable is not independent, it's dependent, because from here you can see at P00 it's equal with 0, but when you multiply P10 times P20 here, it's not 0. Okay, so that's why it's a dependent random variables. Okay, so if the covariance of two random variables is 0, the variables need not be independent. Okay, all right. Okay, so you can do the exercise given here. Okay, we have 6 questions, so at least you try all. Okay, if you have any question, you can ask me. Thank you, class.